that happened in the connection region. So how resources gives us information about the reconnection process itself, and that's why we want to observe as many energetic are solar flares mentioned by was made by people 10 to the power of 17 joules. So it means that the solar flare is 1 billion times more energetic than the most powerful bomb, or it is billions more energetic and very strong. Release a lot of energy. So this is something to remember. And of course, this energy which is released is not only in the form of the solar flare, but usually the solar flares are accompanied by the eruptions of magnetic field and plasma into interplanetary space, and then we call this event coronal mass ejection. And when this coronal mass ejection will reach the Earth, then it causes, of course, a lot of disturbance in the Earth magnetic fields. And these disturbances are becoming more and more important for us as we are a technical civilization. So we have a lot of infrastructure on the ground and also in the space. And this infrastructure might be disturbed or even destroyed by strong coronal mass ejections. And we are mainly cautious about the problems with, for example, communication, because we see that there are some disruptions of the radio communication, our communication with satellites. So, for example, such systems like global positioning system might stop. Of the pigeon in the bottom right, and who is looking for a way. So this is connected to yes, geomagnetic storms has influence on birds or some kinds of birds, because, for example, pigeons, they navigate using the observation of polar magnetic fields. This is really interesting, but this is not the topic of today's talk. It's important, for example, when you have some competitions, because I know that in some parts of the world, the competitions between pigeons and owners of pigeons, let's say, are very popular, and there are some races of pigeons, and for example, prices might be really high at the level of several $100,000. So these prices are quite precious. And for example, when such owner of the pigeon, he wants to train his pigeon, then he is very interested in the state of the polar of the Earth magnetic field, because when we have geomagnetic storm, there is a higher probability that the pigeon will be lost. And if pigeon potentially gives you a price of $100,000, its value is very high. So owners of pigeons are also interested in the state of the Earth magnetic field. This is something unaccepted that I found in in the internet. So, but okay, we are interested in the state of the let's say neighbor of or the state of the surroundings, of the cosmic surroundings of Earth. And we want to understand it, and we want to predict the solar flares. So to know all of this and to have as wide information as possible, we need a new observatory. This was we know that we need some observatory which will allow us to trace all these phenomena from the solar corona to Earth, and to understand what happens. And this new observatory was planned since 1998, so it was quite far, quite far in time. So it was the previous century, and in 1998 it was a conference in Puerto de la Cruz in Spain. It was on the island Tenerife. And the title was Crossroads for European Solar and Heliospheric Physics, Recent Achievements and Future Mission Possibilities. And two proposals were presented there, two solar missions, and one should be chosen among from these two proposals. One was the remote observational platform, which will enable us to observe the solar poles. And the second proposition was the observations of the sun from the shorter distance, not one astronomical unit, which means the distance between Earth and the sun, but from shorter distance, less than 0.3 astronomical units. So after this conference, people just talked, and they decided that instead of choosing one of two ideas, they may be connected into one, and it was named Solar Orbiter, and it was planned to submit to a new call, which was announced by European Space Agency in 2005. Slide. Time from very first to last, namely 22 years. Let's say properties of this mission are observations of the sun from short distance, and even more challenging is observations from the high ecliptic latitude. It means that the solar orbiter will be pushed into the orbit which is inclined to the orbit of the Earth by 35 degrees, and it will allow to see the solar poles for the first time, because we see solar poles, but with very big geometrical effects, with projection, and this is not very this is not a comfort situation for observers, and we still do not know how in fact looked like the areas around sun's poles. So these are things that we are interested in, and this solar orbiter was built, and as Arun said, it is a European mission, so almost every country from the European Union is involved, and also Poland is involved here, and I will tell more about this in a few minutes. And this is a quite big satellite. Its mass is almost 2,000 kilograms. Of course, the scientific instruments are they take only 10% of this mass. The rest is the mass of the entire body of the satellite and, of course, some fuel. And its orbit just started on the February 10th, 2020, and it is planned to make some gravity assist along the path of the solar orbiter, and this assist they should help to push solar orbiter closer to the sun, and in following years to put it on the higher and higher ecliptic latitudes. So this is to get the to reach aims for the mission. Okay, so but of course I have to mention that Solar Orbiter is not the only satellite which provides provides observations from the close distance to the sun. In the 70s and 80s, we had the Helios A and B missions, which reached the perihelion distance of the order of 0.3 astronomical unit. And now, of course, we have the Parker Solar Probe on the orbit around the this is the plan, but it orbiter is the only instrument which has a bunch of telescopes. and why we want to have. So as I said, the X-ray sources, hard X-ray sources, they contain some basic, most basic information about the reconnection process that happens in the solar corona. So I want to observe them in just focus at some point, and we can observe the X-ray is a problem because because X-ray photons have so high energy that they cannot be reflected from any surface. So we have a problem with performing observations in this range of electromagnetic spectrum. They do not provide so nice pictures as you saw in the movie, which was played in the bottom right corner. So this is ultraviolet observations of the sun, and at some point when you see the X-ray sources, these have a shape of some, let's say, blobs of emission. So these sources are not so nice, they are not so rich in details, but it is important that we cannot localize this structure. So building telescope, even if it provide only some crude, not too much details, too many details, so it is important. And we have several techniques. One of them is, for example, the pinhole camera. So just a hole which is in some very specific distance from the detector, and this hole can produce an image, and it is used in X-ray astronomy for many years. For left, you may see the first Polish instrument which was sent to the space. It was 52 years ago. It was built by my older colleagues here in our institute, and it was based on pinhole. But pinhole are also used today as some monitors of the sun, which are based on the pinhole. This is really easy and fast method to obtain some low resolution images of the sun. And also in low energies of X-rays, we have grazing incidence mirrors. So the example is a type of mirrors which not reflect the incoming radiation, but they just allow to change a little bit of direction of photons because of a kind of, and they can of arrays, but it was not repeated in the future. And I just want to say a few more words about, because STIX is based of observation. So how the STIX is built. Catch of STIX in the on the right, on the top right, and in building blocks. So first is what we call the X-ray window or thermal baffle. Next we have imager, and after imager we have see the part of is really, really small. The diameter is the length, the diameter, very small but very sophisticated instrument, and it's 7 grams, and of consumption is about 70 watts. What is exceptional is data transfer, because in such missions like Solar Orbiter, when we have the observatory really far from the Earth, there is not send a lot of data to for STIX is 700 bits per second. So this is really this quota we can just send to the Earth up to several thousand of images per day. So this is quite interesting also. And this instrument, let's say maybe so this thermal, and this is really most important, the temperature balance inside the instrument, because closer to the sun is not easy from the orbit point of view, but also it's not easy because it's getting hotter and hotter. When Solar Orbiter is at the distance of 0.3 astronomical unit, then the front part, the face of the satellite, may reach the temperature up to 500 or even more degrees. So it is really hot, and our detectors, they need to work properly the temperature below -20. So it means that on the one side you have 600 degrees, and 90 centimeters or even 80 centimeters farther, you need a temperature -20. So you have to decrease this all heating, or just radiate somehow this all heat flux somewhere to reach the low temperature of detectors. And it is made in very way. In STIX, we have this special that it works fine, because during last perihelion we have it's just collimator. So each pair of grids is responsible for giving us information about the distribution of radiation on in the solar. I will give the central part is electronic box with very detectors, which means the high resolution, it means 1 kilo and how this imaging part works, how we obtain the images of hard X-rays. So the base for this, let's say the principle for such imager is pair of grids and detector. And this is what we call the collimator. So looking from the right, we have a group of photons, of X-ray photons that coming to us from the sun. And they just meet the first grid, and only part of them may travel through the slits. Some of them, they are stopped by slats. And the population is decreasing, and after some distance, they reach the second grid. And in the second grid, again, some of them are transmitted and some of them are stopped. And at the end, when they reach detector, they are only only survivors are photons which come from very specific direction. So it means that this system is very sensitive for the direction of incoming photons. And in fact, in reality, they are such a collimator, when it measures the radiation, it gives us information about only part of the real direction, only on the part which is perpendicular to the orientation of slits. So this is what it measures. And if we want to have the information about different angles, then we have to change the orientation of grids with regard to the plane of the sky. And another thing, because direction is one factor to be measured, but another one is the size of emitting sources, because we know that they might be different sizes. And this is obtained by changing the distance between slats of the grid. So the higher the slit is, the larger the slit is, the bigger sources we can observe. And the principle is that the pair of grids with the slits and slats, which are also shifted in the phase, then they can modulate the signal from incoming from the sources proportionally to the size of the slit and the distance between two grids. So only with given pair of grid, with given orientation and with specific distance, they gave us information about part of the direction and let's say some a part of possible sizes. So if we want to have observations which gives us information about sources located in different directions and of sources of different sizes, then we have to use sets of grids, pairs of grids, which has different orientation and different sizes of slits. And with such concept, we are able to obtain information which is needed to reconstruct the image. In STIX, in fact, we use slightly different technique because we do not shift front and rear grids in phase, but we tilt them by very small angle, and this tilt produces on the part of detectors, this tilt produce more pattern. This more pattern is just the, let's say, the this is multiplied transmission of front and rear grids. And when we put the detector, our detectors have such 12 pixels. This is because of some specific, this is for more detailed observations. I don't want to go into such details, but the basic measure is the signal which is measured in 4 stripes, A, B, C, and D. And all construction is made in such way that in the field of view of the detector, we have one period of the Moore pattern. So when the source is, for example, changing the direction, then the Moore pattern is shifted in phase, and it can be measured with these 4 stripes and A, B, C, and D. So this is information that we get about the incoming radiation. It looks like this. So here on the bottom right, you have the signal measured in 4 stripes. On the bottom right, you have the real Moore pattern, which is created on the detector. And on the left, you have the location of the source. And now when I will change the location of the source, then you may see that the Moore pattern is shifting in phase. And also these 4 values measured by detectors, they are changing. So we can get information about location of the source. And of course, when we will use different orientation of grids and different sizes of slits, then we have quite rich information that can be used for reconstructing the images. So this is how it works in reality, but not 30 detectors are presented here, but only 12. So how, just to summarize how STIC sees. So we have these front rear grids, they are tilted and it produces Moore pattern on the front part of the detector. This Moore pattern is measured in 4 stripes, A, B, C, and D. And we can just, let's say, fit the transmission pattern or the sine function to these 4 values and to get phase shift and amplitude. And the amplitude, this is presented on this picture, the amplitude is proportional to the size of the observed source for a given pairs of grids, of course. So if source is smaller, then the amplitude is higher, and in opposite, if source is bigger, then the transmission is decreased, and we see the modulation is decreased, and we see smaller amplitude. And also when we change the location of the source, then we see it as a phase shift. So 2 numbers are measured, in fact, by one collimator, amplitude and phase, and they are used to reconstruct images. So the only task left is to reconstruct the image. So with 30 values of phases and amplitudes, we want to reconstruct the distribution of hard X-ray sources at the sun. So we can use many algorithms to reconstruct the image. Here in Wrocław, we have our own algorithm, which works very well with high dynamic range and also with some specific configuration of sources. So I have no time to go into details, but I just want to show you on the right we have works perfectly. And this is what this is the answer of the why on the first slide I showed you that the black screen with only one colorful dot, because this is in fact how sun looks like in the hard X-rays. So we have only emission when strong flares occur, and entire solar disk is just black. Because we do not have too much such radiation, but this dot is really important for us, really precious, because it shows that we can work with the data that we have from STICS instrument. And on the last, this is 2 more slides. So what will be in the future? We hope that everything will work fine, because Solar Orbiter is planned for 10 years, at least 10 years. So we expect that many interesting flares will happen during that time. And we know that STICS is in perfect shape. And until now, we have more than 10,000 flares registered with this instrument. So data is coming every day, and in fact, we need manpower, more manpower to work with this whole set of data, because they are very beautiful, they are very new, and I think that several discoveries are hiding in this set of data that we have, and in the data that we will obtain in the future. So we are waiting for the future. And the last slide I want to show you is, let's say, maybe 50% of people who were involved in the building of STICS, and some of them are scientists which are involved in the analysis of the data. So 100 plus people were needed to build the instrument and to write software and to develop the mathematical apparatus for obtaining this small dot that you can see on the right. And this is all what I wanted to say. Thank you very much.
Thank you very much, sir, for your valuable information regarding different types of instrument to observe the phenomena at the sun, especially STICS. Thank you, sir.
Thank you. Yes, thank you.
Now I would like to invite Professor Rajmal Jain, sir, retired senior scientist, Physical Research Laboratory, Ahmedabad, to come forward for enlightening us with knowledge and expertise in solar and space physics. Professor Rajmal Jain, sir.
Can you hear my voice? Are you able to hear me?
Yes, sir. Yes.
Are you able to see my screen?
Not. Yeah. Now we have.
Are you able to see my screen?
Yes, sir.
Thank you very much, Dr. Devendra Sharma and other organizers inviting me to deliver the talk this afternoon about the solar activity influences on the Earth. I would like to talk about the solar influences on the Earth. Before I start, I would like to say that thank you very much to Dr. Devendra Sharma, as well as the 2 other girls. Her name, I think, Anjali Dwivedi and Anshupriya Singh. So these 2 girls, along with their teacher, Dr. Devendra Sharma, are working on a research project with us since last more than 6 months. And these 2 girls are dedicatedly working during their physics course. So I sincerely appreciate their efforts. I will briefly also present and include some kind of work which they are doing with along with my another student Tushar Kumar Bhatt. So the main student who is working on this project of magnetic complexity, which we believe that is a real source of flare productivity as well as the coronal mass ejection productivity, is actually Bhavin Moide. He is a research scholar under my supervision, and he is basically working at Surat National Technology, NIT, that Sardar Vallabhbhai National. Like to start giving a flavor about the sun. Of course, I strongly believe that previous speakers must have already given a little brief details of the sun, how it works. However, and to designate the fundamental knowledge of the functioning of the sun to the young mass who is attending, like to briefly, you can see this image, and particularly I would like to have of the sun. You can see is
Sir, your presentation screen is not visible again.
Oh, I see. It is lost.
Yes, sir.
Should I share again?
Yes, sir. You may.
Oh. Because in fact, I have come to Rohtak MD University, and I don't know whether I will be able to connect you again.
You are connected, sir, but your presentation screen is not visible. Yeah.
Is it there now? It is there, my screen there?
Yes, sir.
Hello?
It is visible, sir.
Visible or not?
It is visual.
Okay, so at the center of the sun, the brightness is because of the very strong thermonuclear fusion reactions which are taking place. That is, the hydrogen is continuously being converted to helium, and as a result of that continuous reaction, which is taking place at a very high temperature and pressure conditions, almost you can say 15 million degree temperature and very high pressure. So this, under these reactions, hydrogen is continuously being converted into the helium, which are nuclear reactions, and the fuel, that is the whole this hydrogen conversion at the end of it gives the light energy. Now, in terms of gamma rays, and those gamma rays actually, as a result of impact particles or air, which is basically plasma, because of temperature, it is continuously under every interaction loses energy, and that process of losing energy is going on. And till that photon is radiated, that atmosphere is known as radiative zone. And then it comes finally that it has significant energy, cannot give any more radiation, other the energy goes into the convection process, and the whole that atmosphere where the energy is transported from the beneath or that the top of the radiation zone to the photosphere. In between that, a zone is known as convection zone. And then above that, it is the photosphere. From the photosphere is that which we see in the sky. Are you able to see my screen? Yes. Hello.
Yes, sir. But if you disable
able
your
to see
video,
my
then it
video?
will be better. Yeah.
Shall I disable my video?
Yes, yes, yeah. If you can disable your video, then I think the bytes will be used for proper voice transmission.
Let me see. Yes, now. Just a minute now.
I think there is some restriction on internet speed, so that's why your voice is breaking every now and then. I don't know if it is the same for the audience there, but here, yeah, there are some interruptions.
Just a minute. Just a minute. Off or not?
Yes, it is off. Thank you, sir.
And my screen is visible.
Yes, yeah.
Okay, wonderful. I think now it will be better. Thank you for
Yes,
your
now your voice is better.
advice.
Yes, sir.
So the outer portion, sun, that is all what exactly we see every day in the sky, that is photosphere. And this photosphere actually has been, as a function of time, is emitting the light. Please underline this statement. The earlier few millions of years back, it was in the high energy, but now as a function of time, at the current time, it is more actually throwing the light in the visible domain and in the infrared. And as a result of that, the diameter of the sun is really has expanded. And this need has to take place because the sun is now following its birth and then its adultness, that it is actually now growing up, and finally it will die as a red giant. So it is following that whole the principle. Above the photosphere, there is a chromosphere, that color sphere. Basically, we can say that it is on the high temperature side. So if I distribute everything on pressure, temperature, and density scale, then you can see that right from the center of the sun, when outside, that is toward the photosphere, first of all, let us say, then the pressure, temperature, and one density all are decreasing. But after the photosphere, that is when we go from photosphere to chromosphere and corona, the temperature again increases, and there are many mechanisms. Now we have a improved better understanding why the temperature increases. So many mechanisms have been proposed. The one is the continuous occurrence of nanoflares and microflares, and the second mechanism which has been proposed is based on the magnetohydrodynamic waves. And the waves, now it has been offered the mechanism that they take place right from the tachyline or even below the convection zone also. And then they keep on, amplitude is increasing, and finally they dissipate their energy. So that two options are still there, but there is no definite answer till now, and lot of research is necessary. On the other hand, now, as I told, that the whole sun, which is visible in the sky, when we see, many times through the appropriate filters, we can see that the sun actually reveals the dark markings which are known as sunspots. These sunspots are basically the fields, and it has already been shown since last more than 100 years that this magnetic field intensity, their area, and their structure, which is more important, they vary as a function of their passage of this sunspot region. So sunspot region, which we see generally on the sun, they appear slowly with 13 to 14 days, they actually disappear on the back side of the west limb. So generally, is to say, let me give an example, that at the equator, but when about 20 degree, take about degree or so, then it will take 30 days. 60 degree, 80 degrees. So finally, around the pole, it takes about 36 days. What does it mean? It means the sun does not have a fixed rotation rate. Rather, it actually moves faster at the equator and it is moves slowly toward the poles. This is in physics, it is known as differential rotation. That is, the rotation speed of the sun varies as a function of latitude. This happens on both the side, that is at the northern polar side as well as on the southern polar side. Now because of this, the magnetic field which is generated, that is in the convection zone, generally we call it below that taco line, where the magnetic field is generated. This magnetic field is brought up by the convective motion, as well as the gaseous bubbles. Bubbles, just like a water boils and the heat is coming up. Similarly, this spot magnetic field also comes up to these convective motions. Now there are two phenomena in place, which I told. One is this convective flows. The second I told is differential rotation. Now, so convective motion, which is bringing the magnetic field, it is actually smeared up in this differential rotation. So at the pole, which are connected, this magnetic field, that is dipole field, connected through the north to south magnetic field lines of force. It is smeared up in this differential rotation, and slowly, it is actually being split up. That whole dipole field is, the lines of force are split up and it cuts from their main field and it is deposited on the disk, which is visible as a sunspot, and we call it toroidal magnetic field. So basically, there are two different types of fields: polar fields and toroidal fields. The toroidal fields are nothing but the sunspot. The sunspots, now depending on this, how many number of lines actually were there, and number of lines of force per unit area is nothing but what we call as a magnetic flux. So this magnetic flux of this whole structure, that how far this sunspot area was actually generated during this split up, makes the configuration, the structure of the whole sunspot active region. So when sunspot active region is formed, by and large, generally, this has many kinds of sunspots, large as well as small, and both kind of polarities. Northern polarities we call as a positive polarity, and southern negative polarity also. You can see in this picture, which I am showing, and I hope if you can see by this arrow, then you can see within this small sunspot magnetic this structure. Actually, when we see in the high resolution, then you can see large number of sunspots are there. And this is in the photosphere. If you see in the next magnetic field, that is we call as a magnetograms, then also you can see positive and negative polar. There are many kinds of attractive structures. The phenomena are taking place. Very small, actually, white spots and dark spots in the background of the active region. They are known as granulations and dark lanes, etc. I would like to recommend, and I will motivate the students to undertake the research work related to these granulations, this convective flows, this umbra of the sunspots, penumbral of the sunspots, penumbral waves, etc. Nowadays, lot of data from the SDO mission and many other observatories from the space is available on site, and you can take help of some experts and you can analyze in your own college institute, like what Anjali Dwivedi and Anshu Priya Singh are doing with us. The other students also can do similar kind of thing. In a given year is when they are minimum.
Audio is not audible, sir.
Why not? My
Now clear, sir. Please.
can you hear my voice? Yes or no?
Yes, sir. Yes,
sir.
sir. Yes.
And can you see my screen also? Can you see my screen? So this. Hello. Can you see my screen?
Yes, yeah. Just go to the presentation mode.
Can you
We can see your
see?
screen. Yes.
Yes, sir. Yes, sir.
Can you see screen?
Yes, sir. We can see the screen, but not your presentation yet.
Yes, sir. Yes, sir. We can.
You cannot see my presentation.
Screen is visible, sir, but multiple display is open.
Yeah, you have to
Okay.
maybe open your presentation. The screen is visible, so just open your presentation on the screen.
I have opened my presentation.
It's a bit
I have
delayed,
opened my
so we
presentation.
are
Can
waiting
you-
for it to appear at this end. And yeah, now it is visible. It was actually. Yeah, it is visible.
Okay.
Yes.
I think
Thank
it's fine. So what I was saying that between two sunspot maximum time, it takes about 11 years, 10 to 12 years, and the sunspot cycle is known as the 11-year sunspot cycle. And the magnetic field over the whole this as a function of time, it also produce the effects in their atmosphere. So in order to understand this flares mechanism, how they take place, etc., in 2003, under my supervision, a mission was actually proposed in 1998, and ISRO considered the solar X-ray spectrometer mission, the data which is still, being analyzed by many students. Already 4 students have completed their PhD, and 3 more are doing PhD work. So I would like to show the launch of the GSLV GSAT-2 in 2003, which carried actually solar X-ray spectrometer mission and installed it in the geosynchronous orbit about 36,000 kilometers above the Earth. It was a precise and perfect launch from the ISRO side. And the instrument, first time actually it used the 2 different kinds of instrument which were used for the silicon detector and the cadmium zinc telluride detector. I would like to again motivate the students that you are physics students and you should have keen interest in developing the instrument. When I chose these 2 detectors in 1997-98, that silicon pin diode as well as cadmium zinc telluride pin diode, these are both are photodiodes, very small in size. Many people actually warned me that nobody has tested in the space, etc., and they don't have space heritage, don't go to. But on the other hand, the science actually, which we wanted to do, that is ISRO and our physical research laboratory wanted to do the investigation of the iron and nickel in the solar corona, that demanded that we should go for this kind of detectors, which actually reveal the very high energy resolution. And these 2 lines, iron and nickel, the features, they actually are in the spectrum, they are very close by. And if they are close, then how to resolve them and identify. The other question was there also by many investigators in those days, whether really iron and nickel line, that features are visible, that is iron and nickel actually exist in the corona or not. And we wanted to prove that during the flare phenomena, that is at the very high temperature, these lines should appear. And when we did this observations, when it was launched very successfully, and I would like to say that I had blessings of whole PRL director as well as the ISRO chairman and the then president of Dr. Abdul Kalam, who was real motivator for me. So you can see here when we saw this in 2003 after precise and perfect launch, the observations, this time profile from the silicon detector, I would like to have your kind appreciation that even a small flare, which you can see in the black line over here, as well as the big flares were also observed. The different colors in this picture, they are of the different energies. And then we made spectrum, and this was sent by the express telegram to IAU that discovery of iron and nickel in the solar corona. It took place actually during the flare time, and we could prove that yes, iron and nickel exist, and this was done basically employing the silicon detector as well as of course by CZT detector. So we could measure the temperature also, and as a function of this thing, I actually received by recommendation by Professor U.R. Rao and others, Dr. Abdul Kalam, the Royal Astronomy Fellowship of the Royal Astronomical Society on the base of the see. So these two, actually, our whole group approached to determine and to predict what will be the future of the sunspot cycle in cycle number 25. So we approached 2-3 different techniques. So one technique which was a planetary geomagnetic index, AP index, and based on that, it was predicted.
Sir, sorry to interrupt you, but your presentation is not visible. Others can confirm if they also have the same issue.
Yeah, sir. Your presentation screen is not visible.
Can you try to share once more? Now your voice is very clear, so I think it should work from this point. Yeah.
Can you see now?
Not yet, sir. We are waiting. I think it will pop up soon.
I think it will. Are you able to see now?
No, sir.
Not yet.
It will come. I hope so. Because I have. Is it there now?
Yeah, yeah, sir.
So these two groups of working with us, that Partha Chaudhary and Dipali, we used the different parameters, say planetary index, that is geomagnetic index, to use, because I had done long back in 1998 using this AA index, AP index, etc., and made the prediction for the sunspot cycle 23. Similarly, we did for 24 also with my another previous students, Dr. Nipa, and now this Dipali and Partha have done. So we finally, by different techniques, whether we use the AP index or AA index, and even now the new sunspot, the spotless days, that is we call as SLD, and we found by all techniques, 3 techniques, that sunspot maximum number of cycle 25 will be about 100 and not be very significantly high. The other is the prediction that the peak will come around 24, 25 and not early. And when the peak is always delayed, means the sunspot cycle will be big. So this is what kind of, and these papers have already been published. And based on that only, we conjectured the model that perhaps the sun is basically going, or it is moving ahead toward the Gisberg cycle. Now I'm coming to completely a different, now the topic which actually I assigned to students from this RIVA, along working with Dr. Devendra Sharma, to classify the sunspot groups. And they have been doing since last more than 6 months various kind of active regions. I would like to give here only example of only one particular sunspot group which Bhavin Moide has done recently, and show you how really the magnetic complexity works very well to reveal the strong magnetic field. So what do I mean by magnetic complexity? Long back when I was doing my PhD work in 1982-83, and I proposed the magnetic complexity, and the codes which I had used were the separate magnetic actually polarities and their area and their gradient, etc. So basically it is composed of the 3 things. One we call as a Mount Wilson classification, the other is the Boulder classification, and third is their magnetic field intensity. Now, since when I was doing PhD, that is the calculator time, and now the computer came, and now even the large number of softwares are there. So we can actually do much more precise work about this measurement of magnetic complexity. And this is what recently we have done. And we propose the codes for different kinds of magnetic polarities. Say, for example, alpha means it is a singular polarity, whether it is a positive or following. Similarly, beta polarity, then the beta gamma means much more mixed sunspots, which I showed in the beginning. And delta means still the sunspots of opposite polarities are mixed up like that. And similarly, in Macintosh class, that is a Bowler, 3 letters are there, and polarities are there. Then this how much distance from the main sunspot and how much I mean, if they are mixed up that with the opposite polarities, etc. And we measure the magnetic field strength. Magnetic field strength has been measured nowadays by the various kinds of different satellite data, etc. And I would sincerely appreciate my student, Dr. Arun Awasthi, who is currently in Poland. He helped our students both at RIVA as well as this Surat, and we have been measuring. Now, what we did for a 2005 flare, which was observed in November, that flare sunspot group, which is number has been given 10808, and sorry, just for a minute for my throat. In this plot, we have shown that how many total number of different ghost class of flares have been observed by this that occurred in this 10808 active region. So you can see that the large number of C class, that is a mild class, but it also produced the big flares, M class and X class flares. Now, what do I want to say? Why we are studying this? What is the relation with the magnetic complexity? So I would like to show that on the x-axis in this picture, we have shown the dates on which the measurements of magnetic complexity have been done when this active region 10808 appeared on the sun. And in the y-axis, what we have shown is the magnetic complexity calculated based on the table which I showed just now 2 slides back. That so you can see that whenever the magnetic complexity is almost increases by 1 order of magnitude and stays for a longer time over there, then large number of solar flares take place. The color code has been also shown that the lowest intensity, that C class flares have been shown, for example, by green color. M class flares have been shown by the blue color, and red, that is X class big flares. And you can also see that numbers have been written. So many numbers of flares have been observed during the passage of this active region. Now, very interestingly, which we wanted to actually do the research, and that I have been emphasizing these students of RIVA also, that this magnetic complexity, if you plot and if you see that the flare productivity, then the intensity, that big flares, that will increase as a function of magnetic complexity. And you can see here in this, on the x-axis, magnetic complexity is plotted, and the y-axis, the flare index, that the flare intensity emitted in the X-ray in 1 to 8 angstrom is plotted, and you can see that the correlation coefficient is more than 0.7, which is understood still very good. Similarly, now if I consider the stack plot, on the x-axis number of days observed, that is from 7 to 20th November of 2005, and you can see that I think not November, I'm sorry, it is September. Okay, I'm sorry for that. So you can see that the number of CMEs were also very strong. Number of flares were also strong when the MJ. So in the bottom panel, MJ is shown. In the middle panel, it is FJ, and in the top panel, it is CME. So you can see that how actually the various parameters we can see. Now the very important characteristic, this I have shown, is magnetic complexity in the this x-axis, and in the y-axis the CME, only kilometer per second at the speed, but the correlation coefficient is about 0.5. But as soon as I include the angular width inside that velocity, and that is we multiply angular width and velocity and we propose the index, then the correlation coefficient increases. What does it mean? What is the physics behind it? It means the energy is not only governed by the velocity, that is the dynamics, but the spread, that spatial width. So energy, while CME is moving outside, so as a function of the space also, the energy, that material is thrown outside. So what is the angular width also becomes an important in this quantity. Similarly, you can see also in the flare index also. And now I would like to show a very interesting, if you can hear me and if you can just see this picture, I will take a time that at the bottom panel, we have shown from the SOX in the X-ray, the 4 to 25 kV from the silicon data, the X-ray emission on the 17th September, that flare. On the 17th September, that big flare, almost X1 class or M9 class flare is there. And you can see just above that in the middle panel from cadmium zinc telluride detector in 20 to 30 kV, and you can see that the main flare is split up into two parts. You can see that there are two peaks. Can you? I hope you all must, and please note down that in the soft X-ray, when 4 to 25, which is basically dominated by 4 to 10 kV, and you cannot see the two different peaks. But as soon as you go to hard X-rays, that is 20 to 30 kV, you will be able to see. And similarly, it is endorsed when we actually did the plotting of this temporal data of the radio high energy, that radiation, that is high frequency radio emission in the microwave, almost from 8 gigahertz and then 17 gigahertz and the 4, I think 1 gigahertz or something. The boy has, I think, forgotten. It's only 17 gigahertz, and you can see that two, which are cadmium zinc telluride hard X-ray, and still, I mean, we have not yet done 30 to 56 kV. Then it will definitely match with that. What this plot reveal the physics, what was that is during the interaction of the loop, the particles, electrons underwent to the acceleration and it is revealed by both high frequency in the radio waves as well as in the high energy X-rays. While when they come and collide at the chromosphere, electrons, that then the soft X-ray emission is also visible. Many times the flares do not produce thermal emission. They are the very compact flares, but the occur at the groups, due to the very short pitch angle, when the electrons undergo to very high energy acceleration, then they produce this break energy. They reveal it, and we can measure as I showed the break energy in this spectrum in the radio. Although we have done a linear fitting only, but it shows actually the positive parabola is a correlation that toward the high energy frequency has pertained the even the sea surface is increasing, but it is not actually matching with the sunspots. Rather, it is matching with the carbon dioxide emission. And we have measured now almost in last six decades to 7 decades when the India started of the Gujarat and the Junagadh side, and everywhere we found that this sea surface temperature is keep on increasing. So the correlation between the CO2 and the sea surface temperature is more than 0.8 or something. And basically we interpret that the industrialization which is coming up very fast in India in last 50 years, perhaps that produces the CO2 is only industrial CO2 or the galactic cosmic rays also produce the CO2. Research have shown that the galactic cosmic rays actually produces change in the monsoon, change in water vapor, as well as CO2, etc. It means that we must now learn again the galactic cosmic rays in detail. And that is what we have done in the last 4 years, and this is we found that recently two papers have been already published in a very important journals, high impact factor journals. Outside to sea surface temperature is increasing, and as a result of increase in sea surface temperature, the land is actually erosion is taking place, and that's why the sea surface is increasing. So sun is directly or indirectly indirectly through the galaxy influence. You see here village which was here, that village has been in with the government to show that we should take some kind of a precaution. Now, as I've shown, and the study of the sun, you can really measure, and this kind of a Vladimir effect. The sun starts its rising phase. Actually, that dN by dt towards rising phase is keep on decreasing. This is a big alarm. And if dN by dt is decreasing, that is the approach or period required now, because the solar which is actually as a function of the sunspots, now it is decreasing. That number of
your valuable and interesting information regarding the sun and its atmosphere and sun's activity. It will definitely helps the researchers as well as physics. Now,
Thank you very much. Once
have
again,
some
I'm sorry because I am
correction.
in Rohtak. Perhaps I believe that the internet may not be good, but because I am doing through my mobile and I thought it will work very well, but somehow many times there were interventions. I'm sorry for that, but once again I say thank you very much for your kind words. Thank you very much.
Thank you so much, sir.
The
Now we
effective
have some
section. Thank you
correction.
very much, sir.
We have some correction in schedule. We have a short student presentation, and for it, I would like to invite Swati Tiwari, a student of MSc Physics, third sem. She will present a short presentation, very short. Tiwari.
Inviting. Good afternoon to all. Honorable Dr. Rajmal Jain sir, Arun Awasthi sir, Tomek sir, all the professors and all the participants. I am Swati Tiwari, a final year student science in physics from Government Model Science College, Reba. As our great dignitaries have already explained, very well explained and discussed about solar activities and its impact on our earth. So I will take not much of your time, and it's a very short presentation, and it will really help for the new ones that are new to this concepts of what are the solar activities and anything else. So let's start it. So let me share my screen here. So is my screen visible, sir?
Yes. Yeah, Swati. Go ahead.
Okay. Okay. So we are here to discuss about solar activities. So what includes the solar activities is firstly the main important sunspots, then solar flares and prominences. These are the main three types that the solar activities involve. So let's first discuss. So in this presentation, after it, we are going to answer these questions that what are sunspots, what are solar flares, what are solar prominences, and what is the difference between solar flares and solar prominence, and the surface features of sunspots, solar flares, and prominences. And the last but not the least, what can happen when solar flares hits Earth. So let's first discuss about sunspots. As you can see in the left side of the slide, these are the black spots on the sun are called the sunspots. The sunspots are dark, planet-sized regions of strong magnetic fields on the surface of the sun. They can spawn eruptive disturbances such as solar flares and coronal mass ejections. These regions of the sun appear darker because they are cooler than their surroundings. If we talk about the temperature of the sunspots, the temperature in the dark centers of sunspots drop to about 3700 degrees Kelvin, which is when compared to the surrounding of the photosphere, it is 5700 Kelvin. And they typically last for several days. And if we talk about the significance of the sunspots, these are storms on the sun surface that are marked by intense magnetic activity and play host to solar flares and hot gassy ejections from the sun's corona. Scientists believe that the number of spots on the sun cycles over time, reaching a peak. And so it is called solar maximum, as Rajmal Jain sir has already told, solar minimum and solar maximum. And it happens every 11 years or so. It can last for only a few hours to days. or even months for the more intense groups. Now, if we talk about the size of the sunspot, it can be large as 80,000 kilometers in diameter, and it often appears in pairs that are aligned in east-west direction. As we can see here, the magnetic field, when compared to the Earth, it is 2,500 times stronger, and it is much higher than anywhere else on the Sun. The spectrum analysis also showed that the sunspots have a stronger magnetic field, about 1,000 times stronger than the Sun's average. So there is one important term is there is the convective zone, which I will show in the next slides. What happens is the strong magnetic field locks the gas of the photosphere in places and inhibits the hotter gas below to rise to the sunspot. So as a result, the sunspots are cooler. Sunspots appear to coincide with changes in the climate of the Earth. That's why today we are discussing that the solar activities affect the climate of the Earth. Here, in this small video, you can see the black spots, which are known as sunspots. We have already discussed. As I have already told, it often appears in pairs that are aligned in east-west direction. Moving further, now we are going to discuss solar flares. What are solar flares? Solar flares are tremendous explosions on the surface of the sun. These are the intense bursts of radiation coming from the release of magnetic energy associated with sunspots. Flares are our solar system's largest explosive events. They are seen as bright areas on the sun, and they can last for minutes to hours. In just few minutes, they heat material to many millions of degrees and release as much energy as a billion megatons of TNT. TNT is trinitrotoluene, which is used as explosives. And they occur near sunspots, usually along the dividing field. In the burst of radiation is coming due to magnetic energy associated with spots. If we talk about the evidence, first ever evidence, the solar flare was recorded. So it was recorded on 1st of September 1859 when two scientists, Richard Carrington and Richard Hawson, observing suns when they did this in the slides of Arun Awasthi and Tomeksa. Now, on moving further, some CMEs which are accompanied by flares much higher in intensity and much higher in energy. CMEs are huge bubbles of radiation and particles from the sun. Reorganized. The outer layer is convective. So if we go on the distribution of the sun, the parts of the sun, there is one convective zone of the sun. It means it can be considered an analogy to the boiling water, where the gas rolls up and down like in a pot of boiling water. This ionized gas, or we can say plasma, this drags the sun's magnetic field with it, twisting it and strengthening it. In some regions, the magnetic field becomes particularly strong and breaks out into the solar atmosphere as discrete loop-like structures. The energy in the magnetic field is thought to be converted into these things, and this all is done through a process which is called magnetic reconnection, in which the oppositely directed magnetic field lines break and they get connected to each other, and the part of their energy is transferred to the gas in the solar atmosphere, which is seen as the major huge explosions or the intense burst of radiation that come out from the sun. So here you can see how intense and how the radiations coming from the release of magnetic energies can be seen. Moving further, let us discuss about solar prominence. The solar prominence, it is a burst of a huge sheet of gases, also from the inner atmosphere, and it is much larger than a flare. A solar prominence, and we can also call it filament, it is an arc of gas that erupts from the surface of the sun. All the prominences appear to be very bright and hot. They are actually much cooler and denser than the surroundings. Plasma in the sun's corona, that is the outermost layer, prominences are shaped by the sun's complex magnetic field, often forming loops with each end anchored to the sun's surface, that is called photosphere. Long-lived, and it is associated with large-scale magnetic fields, and the second one is transient. If we talk about the typical size of the solar prominence, on the order of 1 lakh kilometer or around 10 times the diameter of Earth. The size of prominence is compared with our Earth. This in this way, this right-hand side of the slide, it is approximately size of Earth. Moving further, if we talk about what's the difference between solar flares and solar prominence, so the solar prominence is anchored to the sun. The arc does not separate and go into space, whereas the solar flare, it will travel through space, and because it is a release of energy. Here you can see on the first diagram, it is a prominence because it takes the shape of an arc. It does not get separated from the sun, and it is called prominence. Whereas the sun flares, these are the intense burst of radiation. Or they travel in the space. This feature, then the sunspots are dark and cold. They are colder. Solar flares, these have high energy and arches. They form like an arc. We have gathered here today to discuss that what will happen when solar flares hit. They can cause heavy environmental disturbance like geomagnetic satellite. Because today in this digital world, our reliancy technology is much these things because this disrupt the GPS and satellite. Large solar flares can cause auroras, which can be easily seen in the northern and of multiple colors. Earthquakes can be attributed to solar activity, and birds and marine life are also affected. In fact, the pilots and the airlines also can suffer with this solar flares. So at last we have reached to the end. Here you can see the innermost part of the sun is called core. Thereafter radiative zone, then convective zone. Convective zone, an analogy to the boiling water. And thereafter chromosphere and corona. You can see here spots, flares, and prominences. So this is the basic understanding of solar activities. That's all from my part. Thank you for listening.
Thanks, Swati, for your presentation. This will really encourage the students who are studying in their MSc classes. Now,
thank you, sir. Thank you, Department of Physics, for giving me this golden opportunity. Thank you so much.
Thank you, Swati. I would like to call my colleagues, Dr. Ashish Gupta sir, for vote of thanks. Thank you.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66, 67, 68, 69, 70, 71, 72, 73, 74, 75, 76, 77, 78, 79, 80, 81, 82, 83, 84, 85, 86, 87, 88, 89, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100, 101, 102, 103, 104, 105, 106, 107, 108, 109, 110, 111, 112, 113, 114, 115, 116, 117, 118 Good afternoon, all of you. Thank you, Sandeep. I feel honored and privileged to get the opportunity to propose a vote of thanks on this special occasion. I would like to thank all the honorable speakers and participants. Words are not enough to thank their constant guidance and support shape of webinar. I am also very much thankful to all program advisory committee and members and technical staff to provide the technical facility without any problem during the webinars. I am also thankful to Principal Dr. Arti Saxena her support of various stages. Today, my words are not enough to express the gratitude Professor for various knowledge about the sun activities. I extend my special thanks to Professor Mojek Sir for given valuable time and share his knowledge researcher and useful. Thanks to Dr. Thanks for HOD sir, Dr. Yash Kumar to give the radiation like a sun to encourage our time to make a webinar successfully. And Dr. Deven Sharma, organizer secretary of the webinar, is providing the facility to engage every persons and students and communication system for the others. I feel proud and thank you for making this
Bittu,
event.
इधर आओ.
Thanks for all of you and well wishes for students.
क्या कर रही थी तुम? join थी?
Research students.
तुम join हुई थी क्या?
Thank you.
पूछ रहे हैं. नहीं थे. Good.
Thank you, Ashish sir. Now it's time to quit the meeting. We will meet again tomorrow, 29th October 2022 at 12 p.m. IST. Thank you, everyone. Feedback link will be sent.
Thank you. Bye-bye.
On your WhatsApp groups.